And this is the second part of the presentation that I gave yesterday. And yeah, closer. Okay. It's sort of continuation, and I will try to be a little bit more applied. Okay, so I will talk more about control and interface generation. And this is a picture just to show what may happen. These are measurements or estimations of the inertia available at intervals of 15 minutes. In Germany, in I don't remember, but it could be 5 years ago. And from 15 minutes to the next hour, it could change even like 50%, which means that the same delta P in 15 minutes leads to a variation of frequency, and in the next 15 minutes, it will lead to the alpha variation of the frequency. So which one we need to consider as dangerous, right? So that's one of the problems with the protections. The protection where most of the Rokov protections, frequency protections, are adjusted, assuming that there is a fixed link between delta P and delta omega, but the problem is delta P, not delta omega. So maybe protection should be adaptive, should take into account that. And then there is this, behind the corner, the limit case. And the limit case in this situation is a strange one, because at this point, there is not even the frequency in the map. So is still relevant to talk about frequency control when we don't have inertia at all. We have only converter interface. Now, I'm going to propose that the answer is yes in this talk, but it has to be a local frequency. So we need to move it from a paradigm where we think of frequency control on the scale of many seconds, and so sort of a unique frequency for the system. I've seen many times this single node models where there is one frequency and everything is connected to a single node. And I said that, yeah, that's okay because the frequency is the same. In the time scale of a conventional primary frequency control, yes, which is maybe tens of seconds. But in the time scale of the inertial response, that's not true. And if we wanted to have a fast frequency control by converters, then at that time scale, there is a different frequency in every point of the grid. And the same way that we have different voltages at every point. And probably we need to get to changing our mind and consider the frequency a sort of local quantity. And this is mostly a conclusion that it can be derived by the model that I'm going to propose. Okay. So let's leave the question open for now. What can we do with non-synchronous generation? Now, the good thing of machines is that they have the synchronous machine is responsible of basically all the possible instability, the traditional instability, voltage, frequency, and transient instability. And today there are other instabilities due to converters, but okay, apart from that, traditionally they were a source of problems, but also they have many benefits. The fact that they have an embedded storage, which is their inertia, which is kinetic energy. Okay, this can be added to converters, of course, but it has to be added, so it has to be based on control. Now, this is an intrinsic storage, and is intrinsically doing the right thing anyway, as long as the machine is connected. This one can do the right thing if the control works well, if the measurements are correct, if we have implemented it right. So we have an extra layer of difficulty here. Sometimes I compare this with the difference between fuses and protections. In protections, so you need to design the measurement system, so the transformers, typically the relays and the breakers. In the fuse, everything is just the one thing. Is the measurement, is the breaker, is the relay, everything in one device, right? So the machine was basically that, was embedding everything inside. So we think of synchronization and the power balance as a sort of synonym sometimes, because the machines do that anyway. Here we also split those tasks. The synchronization is done sometimes by PLLs. The power balance has to be done by controllers that have nothing to do with the PLLs. Okay, so it becomes a more complicated structure. Okay, that might not do the right thing simply because the control is not adequate. So it's an additional layer of complexity here. Okay, but in principle, you can do exactly the same thing Or we can do better, and that's the point, right? What do we do? So we have a blank page. We need to fill it up. At this point, we don't have the constraints of an electromechanical device, which we had in the past. In the past, we had only the problem to say what is the model of the machine. Right? And here we have the problem of we want to define the model of our device, and so it's an addition. It's a different kind of complexity, right? It's like writing from scratch a novel instead of just reading it. Okay, that was what we did with the machine. Anyway, so what are the drawbacks? Okay, reduce inertia. There are probably volatility. The generators are linked to renewable sources. There might be a problem because controls can be very fast, so we can have couplings that never existed in the conventional systems. Advantages, well, we can do whatever we want. So we have the option that we can make the system very good. Okay. At this point, it will be our fault though if it doesn't work. Okay. Instead, in the past, it was it's the synchronous machine, right? We're gonna do better. But now it would be just our fault, right? There is no excuse. There is the same drawback is also an advantage. It can be very fast, so we can probably remove some of the issues that we had because the primary control was slow, for example. Okay. That said, why we should take into account local frequency. Okay, so this is just a very simple model that is the typical model we explain to the students in the undergrad. We say, okay, we have machines, then they start to oscillate with each other. We don't see very well, but it's linked. It's just the picture that is not showing well. And then we discuss, okay, then we have one machine that has this frequency, the other machine has this frequency. But then the network per se, typically, okay, unless we go to EMP models where we have all the dynamics, but in the transient analysis, we say, well, the network has this impedance, but this impedance cannot be that because the frequency is clearly not constant everywhere during the transient. If this frequency, the frequency here is omega A and the frequency here is omega B, it's shut down. The battery might be down. No. Once that you would already change the batteries. It's rechargeable. No, it has the people log in at this moment. Yes, yes. Just 1 minute, we'll get new batteries. Yeah, yeah, okay. No, we'll take the batteries out of this one. Okay, we'll take it from this one. So big batteries in the lab. But last time we met, you said that you were not aware. Oh yeah, yeah. I have a 300 grams of titanium in my arm. So yeah, I'm like Robocop and Terminator. I mean that family now. At the end, yeah. After 5 iterations, yeah. So far, but I think these are also exhausted. Okay, another half an hour will be enough, I think. Yeah, that's it. Okay, so clearly this is sort of inconsistent. Of course, in the conventional systems, so the frequency cannot change that much. The rotor angular speed of the machines is always varying just a little with respect to the synchronous reference frame, and so we can approximate the reactances as constant. Right? They are not, but The point is that the model of the network assumes that the frequency is the same everywhere and is equal to 50 Hz. But then the machine model says exactly the opposite, that the frequency is actually depending on where you are. So one of the starting points that I had when I started to look at the frequency was very simply, I had the simulation tool that I developed with my students, my collaborators, and we wanted to be able to take the frequency at any point of the grid, because at this we wanted to make a frequency control through non-synchronous devices, and so these non-synchronous devices do not have a rotor, and so we couldn't use one of the variables of the machine or the device itself to know what was the frequency there. So we said, okay, we need to invent somehow how to measure that. Of course, there are techniques. So you can use washout filters, so you can just use the angles of the voltages and make a numerical derivative of that. But we wanted to do better, and so all the discussion originated from that question: how do we actually implement the frequency? So we started with a model that was trying to make an interpolation of the omegas of the machines and say, okay, if omega is omega A here and omega B here, then in this line, if it's passive, there is just an interpolation of that. So that is the idea of what we call the frequency divider, which is a sort of a divider for frequencies instead of for voltages. Okay, and that was okay, but then since I wasn't satisfied, we got to the complex frequency definition at the end, okay, which, because we were neglecting all the voltage magnitudes and the fact that that is interacting with the phase angle as well. Okay, so well, this is just a case where we show that in fact the frequency is not the same everywhere. This is the Turkey, and these two lines indicated the separation of the grid. Now there was a huge swing after that, and that have impacted neighboring countries. We don't have a measurement for that, but I was working with this TSO in Romania, and they had the measurements for from the PMUs. They were showing that depending on where the PMUs was, the closest to Turkey, the bigger the frequency variation. That's okay, that's expected. But the point is that from my model in the transient stability analysis, I couldn't see it, because from my model in the network per se, the frequency was exactly 50 Hz everywhere. So, okay, we know that the frequency changes. How it changes? What kind of model can we do to calculate the actual frequency everywhere in the network? Okay, let me switch that. And why we want to do that is that because we have devices that may need to measure the frequency. The problem is also that we don't have only synchronous machines. If we had only synchronous machines, apart that we would have immediately the answer, because it would be the rotor angular speed. But there are easy ways to calculate the frequency if there are only synchronous machines, because we can just take the omegas of the machines and then do some kind of interpolation. But again, that would be what we call the frequency divider, right? So that was an immediate calculation to do. But then when you have devices that are active and they may, they do control, and so whenever you have a control, you have a device that is varying the frequency that the bus where is connected, right? So the only single device that doesn't impact on the frequency is an impedance, which is the only totally passive device. Any other, even if it's in minimal part, but it will impact on the frequency, because it does not respond passively to the variation of the grid. It does not take in any variation, but is trying to counteract it. And this counteraction, which is typically control, makes a difference in the frequency. So we need to take that into account to know what everything else, how everything else is affected. So how do we take into account these effects of every device connected to the grid and the grid? Okay, then we have other problems, that is how to control these devices. Okay, say that we actually have a good measurement, we have a good way to estimate it, and we have a good way to calculate local frequency. What do we do with it? And here is all the problem on the control. So it's kind of, you know, this following issue is, okay, I have the measurement, I do want to use it in a proper way. And I'm showing here an improper way to show that it's not always so simple. Now, this is the case of a large wind power plant in Ireland. So these are actually measurements, okay, from the system. So they designed the controller for only for the case when the power has to be reduced because of frequency control. So there is no reserve, but they can reduce the amount of generation. That is easy, okay? It's just switching off some power plants or reducing, then PPT. So it's easy. The point is that they don't want the power plant to do all the time the control if needed, but only if the frequency is outside the dead band. And the dead band is the problem, because what happens is that this wind power plant, now it's Ireland as well, okay? So a large power plant can actually have an actual effect on the frequency. It's not just providing a little bit of power. Any big power plant can change the frequency in a way that if it's effective, and this one was effective, was I would say, was able to bring the frequency back into the dead band. But as soon as that happened, then the controller would stop. But at that point, the frequency would go again outside the dead band, but then the controller was acting again. And so this was a sort of flapping or cycling, but it's called flapping in many control applications. That is due to the dead band. If there is no dead band, it doesn't happen. But the problem is that the dead band was part of the grid codes, and it was also because you don't want the wind power plant to do, to lose power just for a small variation of the frequency. And of course, it was also the problem, a problem due to the fact that the power plant was big enough, and it was controlled like all controlling or nothing controlling. There was no granularity. It was not like, okay, there is not so much need, so we can just down power some of the turbines. All of them or none of them. And so this on-off behavior was the problem. I think the solution is to granularize the control, so maybe some power plants doing it, depending on severity of the contingency. But you see, you enter into problems that didn't exist in the past. So the solution that is, we do control with non-synchronous generation becomes a new problem. And I cannot imagine what would happen if the control was very, very fast and interacting with dynamics that we don't even know that they are there, right? Because of never interacted. This is a simulation, okay? I'm not saying that the IEEE system is unstable, okay? I'm really not, but the simulation was, we tried to make a 100% non-synchronous generation, okay? It is, of course, just a theoretical scenario now, because it's not allowed in the system. And we used the different approaches. So, okay, with the synchronous machines, it was stable. We knew that. Then we tried a different kind of converter controllers, virtual synchronous generation. I and O is if the signal was inner or outer. It's just a detail on where we put the controller into the the converter of the virtual synchronous generator, and then the classical droop control. Now the droop control was unstable, okay, and with partially virtual synchronous generation controlled power plants, then the system was stable, and actually could also be much better stable than the conventional one. Okay, now probably it's not super clear here, but yeah, you see this swing that is very pale is the conventional system. With virtual synchronous machines, we can be faster, and so it was better. Okay. Anyway, so this was one case. So we might not be able to use the droop. Now, I'm not saying that the droop will not work. In this case, it didn't. Probably if we tune it better, it would work. But so again, problems, right? Because with synchronous machines, the system is always stable, basically. It's really unlikely that our system becomes unstable for the contingency. Once I tried, and the student say, look, I'm leaving the fault for 2 seconds, and still the system doesn't lose synchronous. So I called the people that I knew in energy. Say, is this, it's my model that is not good enough, or no, it's okay. You know, they don't have, you know, you really needed to do a disaster to make it unstable. It was built with a lot of redundancy. Anyway, so then they have, this is from Air Grid, okay? They have this concept of frequency quality. So they wanted to keep the frequency within certain limits, and any time that is not respected the limit, they consider it as a lack of quality, and they have measured this lack of or loss of quality in during the years, and they saw that you know, these are the limits. Okay, as you see, they are different from the European community, like NSOE and network, typically, you know, bigger because it's an island, and it's a small island. I have an FDR, this frequency disturbance recorder from Tennessee, and once I installed it, after a week, there was you know, Leo that called me and said, "Do you have a blackout or what?" You know, and because we had some event that was normal, it was just a little bit of wind, right? But disconnected or the internet is not working. Yeah, exactly. And but it's just because of for the ID system, the limits are way bigger than usual, right? So anyway, even so, there are violations. Okay, the system doesn't really collapse, but there are more violations of these limits, and so they found out that this plus or minus 200 millihertz limit has been again. No, now we have to work. Energy hungry, right? Yeah. Fine. Thank you very much. Thank you. So now this is just to say that along the last 3-4 years, they have noticed that this increase in the number of periods of high non-synchronous generation share in the system have significantly deteriorated many of these metrics that they have, and they link that specifically with the problem of the inertia, or at least whenever there is a high penetration of a non-synchronous generation, they see most of the frequency limits are not satisfied, or whenever there is an increase of the violations is because of the periods of a high non-synchronous generation. Now, it might be the inertia. We can call it the problem of a low inertia system. It might be because of the lack of some kind of control, but there is a problem, and so we want the solutions. Okay, so this is a start of motivation why I'm talking about what I'm going to talk now. Okay, complex frequency. After the differential geometry that I discussed yesterday, this will look simple, okay, because it's just a complex quantity. It's just an extension of the conventional idea of frequency that we have, which is one scalar, to a complex quantity that has, in fact, 2 elements. Okay, so it's 2 numbers instead of 1. How we get there? Okay, so the point is, I want to use the power flow equation during the transient. So I write just the power injections into the grid. But I take into account that in the meantime, there is a transient, and so the voltages and currents are evolving somehow because of the transient. So I do the simulation, and I'm not substituting it, I'm just doing it, but I take into account that this will imply that I have variations of V, current, and power injections. But the balance has to be kept all the time. So we will need to have that whatever happens in the devices has to be balanced instant by instant in the grid. Okay, then I write the voltages in this way. I use what yesterday called the park vector, but at the end it's just the 2 components of the park DQ axis, and I call it a complex number, just summing up the two things. Since they are on different axes, I use J for the Q. It is a very useful quantity because in steady state, this becomes what we know, which is a phasor. Okay, so if we don't have dynamics, the part vectors downgrade to the classical phasors that we use in power flow analysis. So it's kind of a generalization of the phasor in dynamics. It's not the dynamic phasor that is defined in some papers, because if the model is taking into account electromagnetic dynamics, we still define just this vector. So PARC, in principle, retains all the dynamics of the system. It's just a transformation. So PARC is defined starting from EMT quantities in reality. Okay? So now here there is a simplification, which is the only simplification that I'm doing. And in recent works, which I'm not going to present, I'm trying to remove the simplification. So it's not necessary. It's just the one that I'm using here. Is that we can still define the admittance matrix. And then here you can say, but you have just said that the problem was that in the admittance matrix, you were considering the frequency was constant, and now you're using it because otherwise you cannot do. Yes, that would be, it seems an inconsistency, but it's de facto, I prefer to call it an approximation of second order. So we introduce an approximation, but this approximation is affecting only higher order of the equations, because we are going to take a derivative of this. So it would affect only the higher orders component. So it's a small error. So it doesn't really affect the calculation. I tried to see what happens if we don't use this approximation. The difference is so minimal that is, in fact, a very good approximation. Okay. So with this hypothesis, then I can write a currents in this way. There is no time dependency here. So that's the idea. Okay, that's the only approximation. Everything else of the model is whatever you have for the machines and the converters. Then we write the voltage in this way. And this is what I was saying yesterday, one question, I guess. So we can write dq coordinates, we can write polar coordinates. I'm using this exponential coordinates. Okay, so theta is as usual, but u is the logarithm of v. So with this trick, then we can easily see that when we do the time derivative of v, we will have the derivative of u, derivative of theta, but then we can write this. So we can write that the derivative of the voltage is the voltage by this complex frequency. I call eta the complex frequency. So eta is the conventional derivative of the angle, and this derivative of this component u, which is sort of exponential magnitude, if you like. That is the rho that we saw yesterday. So it's v prime divided by v. Okay, it's exactly the radial frequency that I discussed yesterday. But when we do this calculation, and then we can substitute it here, so we can find that also the current is a function of the complex frequency of the voltage in this equation, because we neglect any possible dynamic here. If there were dynamics here, we would have a component that is due to the variation of y with respect to time, that we can call complex frequency of the lines, or complex frequency of the elements of the lines, and it would be an additional term. What is the benefit of doing this derivative? And this is a common, how to say, thread for all the discussion, that when I do differentiation, and so this is also the starting point of all differential geometry, the differentiation is done because that will lead to linear point equations. Okay, so point means that are local, so valid at that instant, but every expression that I get is linear. Is linear time variant, because it depends on the trajectory, but is linear. So here we have, okay, this started linear, but it will be linear anyway. Okay, so when we get to the power, we also have this expression that is linear in the complex frequency. Okay, And so we have this expression is the power flows in every single line of the network multiplied by the conjugate of the complex frequency of the voltages at every node of the network. We miss the other side, so we miss the injections of powers from the devices, and that would be the link between, let's say, the topology of the system with the specific dynamics of each device connected to the system. Okay? I like to think of it like these relativity equations that are on one side the geometry of the world, and on the other side the forces that are. So you can think in the same way. This is the geometry of the world, topology, and then we need to link to the forces that are applied to it. Okay, and the forces that will modify the space because they modify not the topology maybe, but the way the topology interacts with the rest of the forces. Right. So we need to make a balance of that. So we can have, after a little bit of tedious algebra, we come to this expression. So we have the time derivative of the power injection. Okay, so this depends on the states of the variables. Okay, the states of the devices connected to the grid, their power injections, data, so again the frequency, and the network. Okay, so we need to define what this is, because this is a function of state variables, possibly again of eta. Okay, so how do we find this in a very systematic way? We can, but let me do a little bit of one interlude here. That is the following. When we define the frequency of the voltage, we have seen this expression. One of the things that confused a lot the reviewers when they sent the paper on complex frequency was, yeah, but if you do all your, if we accept your calculation, then the frequency of the current is not the same as the frequency of the voltage. It was like, it cannot be, but it cannot be in steady state. In steady state, everything is the same, so it has to be the same everywhere. Current, voltage, doesn't matter. In transient, it can be whatever you want. So the point is that in transient, the eta of the current, so the frequency, the complex frequency of the current, can be completely different from the complex frequency of the voltage. It can be nothing to do. Think of the simplest scenario is when you have a regulator where the magnitude is constant. You need to change the current if you wanted to keep the voltage constant. If nothing else, because you might need to inject a different reactive power. At that point, you will have that the rho of the current will be not zero, but the rho of the voltage, assuming an ideal controller, is zero. So if nothing else, that is different. Okay, but it's also omega different. So also the frequency is different. And to think of it, you may think of maybe like two devices that are connected to the same bus. The sum of the current has to be, make the balance at the bus, but each of them can be one, counteracting the other. So one can have a variation that is positive and the other one is a variation that is negative. The balance is still the same. So the current can be really, during the transient, whatever you want. Yeah. Whatever you want within limits. Limits of the control. Yes. Yes, they cannot be totally so. Not independent. Not independent. Exactly. The link is due to the controller that you have or the device that you have connected to the grid. Exactly. That's a perfect point, because in fact I have a student that is working now on synchronization, and we are defining synchronization as the deviation of these two frequencies. Okay. So anyway. Now, I'm not talking about the current now. I'm just using the frequency of the voltage, assuming that the currents are linked to the voltages through the network. Okay, so through this admittance map. We're still looking at the derivative of the complex power. Has to be independent from the network. We want the derivative of the complex power as function of the device equation. And every device can be described in this way. So it has internal variables, state variables. Y can be also the voltage of the point of connection, or any other variable that is in the device. But in particular, it can be P and Q of the device. Okay, so that is the point. So I can express the derivative of P and Q as algebraic variables as a function, as you see, of the states and the differential equations and these Jacobians. Now, this calculation can be very complicated, can be simple depending on the controller, but can be always done. Particularly can be done during a simulation or offline, because we have these equations in a model, right? And we can always do that. Then one can say, okay, so your model is not working with measurements or as black box model. Yes, it is. You just know V and the current. At that point, you can calculate the power. Using the product of V and I, and then you can calculate the numerical derivative of it. So in either case, we can calculate S prime because it's completely independent from the rest of the work. It's whatever we have at the bus, and we can calculate it just with the measurement of V and I, or with the model. Okay, either way. Okay, I will use the analytical way because it's more relevant to what I want to say. So again, after a little bit of tedious matrix manipulation, we have that the device side can be always written in this way. You see that it's always linear with respect. So this is the derivatives multiplied by this. So it's linear with respect to eta. Then it depends also linearly on Z prime. But this expression is always this structure, as always this structure. You cannot have any other. It can, this derivative can be just constant, so it can be very complicated functions, but it's always there. Okay? So we have an expression that links every single device rate of change of power, rate of change of complex power with the complex frequency of the voltages everywhere in the network. So in principle, we can calculate eta, knowing everything else. And since it's linear, it's just inverting a matrix. It's a time varying matrix, so we need to do it for every time step. But we can do it, we can calculate it all the time. So in simulations, it's just a quantity that we can calculate with analytically, basically, with the precision of the integration. In practice, okay, we can do the measurement. So we can also calculate that just calculating V and the derivative of V. So we have that. Now, consequences of this formulation. The consequences are interesting because we can write, since it's a complex expression, we can write two components. The sum of that is what we have found so far, but there are always two components. One is function only of omega, so the conventional frequency that we know, and one is a function only of rho, which is this radial frequency that depends on the magnitude. Note that S1 and S2 are complex. So there is an active power component that depends on omega, and the reactive power component that depends on omega. There is an active power component that depends on rho, and the reactive power component that depends on rho. So, depending on how big are these coefficients, yes? Which expressions? The top two? Which operator? Ah, the dot is the element by element product, because they are vectors, okay, for every bus. And so this is yeah, like MATLAB dot asterisk. Sorry, I didn't say. The bold faces lowercase are vectors. The bold face uppercase are matrices. The bar is when it's a complex quantity. I try to stick to that. And since sometimes I use the dot as a derivative, I took out the dot from the J because for me it's super confusing to have, you know, sometimes the dot is just J and sometimes it's a derivative. But anyway, the point here is that we have two. So for every device, the power can be split in active and reactive, or as we see here, in two complex quantities that are split in the way they affect the frequency. And of course, it depends on the control and it depends on the device. So maybe the part of the imaginary part of S1 that depends on omega may be super small, but we control, we can make it as we want. So the message here is that in practice, we can, and this is probably known anyway, there is always, even if it's weak, a link between Q and theta and P and V. Here we are saying that there is a link between the derivative of P and omega and the derivative of Q and omega and so on. So it's not completely new results. The novelty is that in distribution systems where the resistances are not so small with respect to the reactances of the lines, and with converters where the frequency control can be in the same time scale of the voltage control, then these links, the cross links between Q and omega and P and rho are stronger or can be made stronger. So one of the things that I'm going to propose or to show is that instead of doing the coupled control, Q only V and P only frequency, we can do both also at the same time. But if we do it right, we can make it better and then the usual control. Of course, it doesn't work for synchronous machines because synchronous machines have a sort of time scale decoupling between frequency control, which is typically slow with respect to the area. So they cannot really couple that much because of the time scale. But if the time scales are in the same range, then we can do decoupling. And it's not that bad. It can be good, okay, in some cases. Now, I show you some examples. And this for me at the beginning was really interesting because the fact that we can think of P and Q as the sum of two components that have different meaning for the network was a kind of discovery for me. And for example, in a constant power injection, we have by definition that the variation of the complex power is zero. But that doesn't mean that the two components are zero. They are just the opposite. They are not zero. They are just perfectly compensating each other during time. Because to have a constant power injection, we do need a control. We do need that whatever variation of the voltage will reflect into a variation of the current. And that is an active action of the device. And so these two components are not zero, even if the result is zero. This is another interesting component because it's the only passive device that you can find. It's the only device for which, for sure, S1 is zero. We can demonstrate it. I just put the result. It's possible to actually prove it. It's not just I'm saying it. It's mathematical. It's coming from the questions. And it's the only device that exclusively only has two all the time. Is there a component that is the dual of this? So is there a component that is only S1 and that does not have as only 0 S2? Yes, is this kind of a device. It's a device that has constant current magnitude and a constant power factor. If you calculate it, that is the only device that has exactly the dual behavior. Now, this is the power that affects the frequency. So when you control a device in this way, according to this equation, it means that whatever you do with P and with Q, you will change the frequency. So you can do effectively, in this case, a control of the frequency with either P or Q or both. That it will be affecting in the same, provided that you keep perfectly constant the current and perfectly constant the power factor. And of course, it's also what's good. Yeah. Yeah. No, yeah, exactly. But the interesting part is that if you there are this idea, I agree with that, but there is this idea that the green formula has to regulate the voltage to be able to regulate the frequency. But in reality, what you really need to do is then you can be the most effective possible because there is no part of S2. So whenever you have, say that you want to regulate the frequency with P, if what you really should regulate is P1, the part of the S that is affecting omega. But if you regulate only P, you will change P2 plus P1. And so part of the regulation, everything that is in P2 will not be effective, will be lost, will be like an inefficiency of the control. So we can try to make controllers that are more efficient, just trying to minimize if you wanted to do frequency control, minimizing P2 or Q2, depending on what you do. And then the other way around, if you want to maximize the effect of the voltage control, you need to minimize P1 and Q1. It's a completely different way of seeing it, but it's still based on conventional equations, right? It's not new, it's just the derivative of power flow, right? So it's just a consequence of it. And in fact, if you do some approximations, you see that there are these links, okay? This is the classical DC power flow, the derivative of the classical DC power flow. And it's okay for a DC network. Now, if your network is, has a very low losses, then this link is super marginal, and you have maybe a strong link between voltages and Q, which is the typical thing that we say, right? Notice that this works also in DC. In DC, you would have that omega doesn't exist, it's always 0 because it's DC. You would have that B is 0 because omega is 0, and so you don't have admittance this with the imaginary part, but you still have this part. And at that point, the only thing that remains are the losses. And at that point, you see that the only way is to change P2. You have only P2 in fact, and only the variation of the magnitudes of the voltage. So this is perfectly consistent. So in DC, it's just the same equations. It's just that you remove this one because there is no Q, and you remove these ones because there is no omega. But there is another thing. If your network is very resistive, then this becomes important. There is a case where say that the two terms are equal, like, but probably not exactly in a medium voltage network, but in medium voltage network, you have a bigger effect of resistance. But say that they are same matrices, okay? So equal. At that point, you can equally impact omega and the voltage using equally P and Q. It would be, and if the network were more resistive than reactive, then you better control the frequency through the reactive power, which is kind of strange thing to say. But if your network were for any reason more resistive than reactive, then you should do that. Okay, probably is also very well known, but it's confirmed by this analysis. Okay, now this is the caveat that I was mentioning at the beginning. Okay, so this is the part that I didn't originally included because when I was presenting the general meeting, the people was looking at me with a strange faces. So I said, well, okay. But then I saw that there might be interest, so I presented take it the way it is. Okay, it's a sort of strange thing. Okay, so the question here was, okay, we know that in synchronous machines, there is an internal frequency that is the rotor angular speed, and that is a physical quantity with differential equations that describe its dynamic. Okay, so I was asking myself, is it possible to define a similar thing, a similar internal omega for any device? In fact, not just synchronous machines. Why not? So the same way that we have the classical model for synchronous machines, where we have an EMF behind the reactance with a delta that is basically the angle when you derive it, you have the omega. Okay? Can we do the similar model for converters and take into account the control that they have, put it the right equations to write that, say, classical model for converters? Now, the answer was no at the beginning, when I was thinking only at the frequency as a scala, like just one quantity. But the answer might be yes if we think of the frequency as a complex frequency. At that point, we have both terms that takes into account Q and P and takes into account of magnitude and phase. And so at that point, yes. So some models are only using rho. Some models are using both rho and omega, but they are basically equivalent to the model that we do for the machine. In fact, all this discussion can be also applied to the synchronous machine. In the case of the synchronous machine, we would obtain the classical model of the machine with the reactance behind, with the EMF behind the reactance. I don't talk about it because that is the result. Okay. What happens when we don't have a synchronous machine? Now, why we want to do that? Well, it was an exercise at the beginning, but then maybe we can use that to do control. In the synchronous machine, we do measure the angular speed, not the frequency of the voltage at the bus. So if we knew the equivalent internal frequency of a converter, would that be a better quantity to control rather than the omega at the bus of the converter? That was the question. Okay, I didn't know at the time, and but before having the model, I couldn't try. So, and the answer is probably yes. It's better to actually estimate this internal omega, the same way that we actually use the internal angular speed of the machine, not the omega of the bus. At this point, I needed to use this information that in general, during the transient, the eta, so the complex frequency of the current is not the same as the complex frequency of the voltage. And the only case when they're exactly the same all the time is for constant admittances. Again, it's a special device, okay? So, but it's a device that does not provide control by definition, so it's also not useful in my case, okay? So the model in this case would be nothing, just the admittance. There is no EMF there, so it's still quite consistent in the discussion, right? Now, the point is that the complex frequency has two components, and that's why it's useful to do this kind of modeling, because in the machine there is only a rotation, okay, and then the field voltage can change the magnitude of the EMF, but they are separated somehow. They are completely two different channels, because one is the mechanical equation, the other one is the field winding equation. In the converter, they can be mixed up. So the complex frequency takes into account that there is this translation, which is the rho side, and a rotation, which is the omega side. Okay, so the combination of these two between voltage and current gives the behavior of the internal frequency or complex frequency of each device. Now, we are going to discuss it as a power injections, again, with this S prime, but instead of using the formulation that I gave before, I'm going to use this one, which is, you see, this is the complex frequency of the power, of the complex power. Is the sum of the complex frequency of the voltage and the conjugate of the complex frequency of the current, right? Now, here you see that sometimes they cannot be the same. It's very obvious now, because, for example, if you have a constant power injection, then these two has to sum 0. And so they cannot be the same. Otherwise, they would be twice eta, right? So here I do some examples. For ideal constant current control, I have this. So here is also, again, evident that they cannot be equal, because this would not be necessarily 0. And so you have that this is not 0, but this is equally 0 all the time by default. If you have a constant current source and constant power factor, then you have this link. So they are actually equal, but only in the rotational part. Then the radial part, as you see, must be different, okay, by the controller definition, ideal controllers. Then constant active power, you have this, so you have that they are exactly this expression. One would say Hermitian, but okay, is the way they are, okay, the minus of the conjugate. And then the constant admittance is the one that we would think if we were asked, without knowing all this theory, we say, what would be the frequency of the current and the I also responded myself, they must be the same. But why? Because we think linearly and we think passively. We think in this way. There is no, we think the simplest way possible because it's the way that works most of the time. But our systems are non-linear, and so they don't respond to our intuition. Okay, but this is the intuition that we have because we think linear, and the admittance is linear. Okay. And then there are strange situations like this one. So you can complicate the thing as much as you want. Okay, you can do the exercises. It is fun. It's helping for the discussion, right? Because then I say, okay, now we do this exercise of saying that I have an EMF behind some reactance. Okay, the reactance is something that can be defined based on the control and the model. It's not a physical thing most of the time. It can be virtual, of course. And this is not existent necessarily. Is this internal EMF I need to take into account, so a sort of series connection. And this is the physical one. So this is where I have the physical voltage, the physical current. And here, whatever difference there will give me the internal omega or the internal eta in reality, not necessarily only omega. So, okay, here I put some additional equations. I don't remember why I put this one. Yes, because what I want to say is that I'm also assuming the classical model. So I'm assuming there is no losses in the VST, the same way that we assume no losses in the machine. This simplifies the discussion a lot without losing much information. Because, okay, there are losses, but are irrelevant. And so basically we can have this equality where the hat is always the internal one. Okay, so the hat means the fictitious internal quantity. Okay, so let's see what a different part of the controller. You remember that the converter has many different things that we can be there, cannot be there, depending on the control that we want. So the first part is the PLL. What is the effect of the PLL? The PLL is just a rotation. It's a little rotation that depends on how fast it is. It's very similar to what the synchronous machine does, but the time scale is completely different. So if you do the calculation with the synchronous machine, here you obtain the omega of the rotor of the machine, okay, the angular speed of the machine. The difference is that in the PLL, the time scale is 1, 2 order of magnitude faster than the one of the synchronous machine. So it's typically a very fast transient that you might also neglect if you want. But it's in fact a little rotation. Now, the linearity of this approach, because we differentiate, means that any components that we add will add a term, not create a nonlinear function. Will just be an additional thing that I am adding to it. So this can be there. If we assume an ideal PLL, then there is no difference between the two things. Okay, but if the PLL is not ideal, is introducing a transient rotation. Okay. What happens with the inner current control? Well, after a little bit of calculations, now here I need to do what I typically criticize that the control people do. That is to do, let's say that all the lines are the same. Let's say that all the generators have same inertia. Let's say that all loads have exactly the same power, which, okay, do it, but then it's not a power system, right? But okay. Here, to simplify a little bit the discussion and to show some neat result, I'm assuming that the gains of the inner loops are equal. So Kp of the D channel is the same as Kp of the Q channel. Now, might be not true all the time. Let me use this approximation. I know I'm like the control people theory, the control theory people. Okay, we share the same scene. So, but if you do that, then you obtain this coefficient that is just this ratio. And the effect of the inner loop is only a translation. Okay, so when we combine it with the PLL, we have the rotation of the PLL and a translation due to the inner loop. So that's the only difference that you get. Okay, so you see there is this additional term here. Okay, so you can make it 0 or very, very small. If this ratio is very, very small, you can say, I don't need to take into account, but it's there, and you can assume that. Then there are so many controllers that the list could be very long. I just put some of them. Now, what happens when I have a voltage feed forward? Okay, when I have the voltage feed forward, then I obtain this expression. So is again linear is always linear in the constant frequency. The coefficient of it can be complicated things, but so it's not always so simple to say is a translation, is a rotation. Is typically a mix of the two things, and the more complex the controller, the more complex is this link between translation and rotation. And so here you obtain these terms. So it introduces both of the things in some way that makes sense for the control. Okay, this voltage feed forward is something that is done to decouple a little bit the IEQ and ID controllers. Okay. Now here probably most of you know much better than me. I was just taking whatever has been done and not really into these details of the converters. Then we studied the grid following controllers, and we obtain this kind of relationship. Okay, take it as they are. Okay, is what it is. Okay, but always we can end up, you see, with some coefficient that multiplies some of or the complex frequency or some component of the complex frequency. And grid forming is the same. And the grid forming is a little bit tricky, because at the end of the grid forming, if you take the ideal model, it's like a synchronous machine. So there's nothing really to say. The internal omega is what you get as internal. So this virtual variable that is the virtual angular rotation is what you're looking for. But we found some other relationship with this, internal quantities, but they were fun. Were symmetrical somehow. I like symmetry. It makes me feel happy for some reason. So we defined that. Okay, so now we go to some applications. Okay, some case study to show. Well, first this modeling. First, some observation that they were how different the internal frequency was with respect to the outer frequency. Of course, it depends on the controllers. So it could be used to tune it, tune the controllers if you like. Was just an observational part. Then we did let me see, the effect of it. So basically we did sensitivity analysis. Okay, so we can make it the effect very big or very small. It's something to know, if nothing else. What we can evaluate it and quantify it precisely. Let me see if I have an example where I can show that we were. So at the end, the original question was, would it be better to do a controller using the internal omega instead of the one that I measured at the bus? I think that I put an example. These are still, how to utilize the complex frequency. Okay, so to make the controller more effective, so we use this internal frequency, and okay, it depends on the control again, but we were able to make it, this black lines tends to be better than the gray lines, which oscillate more or are, you see, here is also unstable. And that was simply using the internal frequency, of course, with different parameters. Okay. Is it useful? Well, maybe not that much if we just use controllers that already exist, right? So the idea was maybe is for the design of new controllers. Okay. Yeah.
Here you are trying to provide some inertial board using the internal frequency.
No, not necessarily. I was using just conventional grid forming, grid following.
For the grid following, because you are talking about the PLL, how would you estimate this internal frequency?
Well, in the simulation, I can calculate it very precisely. So I took that. Yes, I didn't made in the model the estimator that estimates the internal frequency. I calculated in with the formula that I showed, which for a simulation is easy, right? And I took it. It could be, if you like, if not as a practical application, you can say, if I were able to calculate that precisely, would that be better? And then you can show it. If it's better, then you may want to do an estimator that estimates that internal. If it's not more convenient to use this internal frequency, then you don't need to do it. But the first step was to have with the ideal signal, say that you have it, okay? I'm not saying that it's possible, I'm just saying that if I have it, and in the simulation I can use it, would that be a better thing? In some cases, it was, okay? Of course, it depends on the controller. Then you can say, okay, I can tune the controller in such a way that the external signal, the one that I can actually measure, is the closest possible to the internal one, okay? You can also do that, if that makes sense. So it's more for the design, okay? And it wasn't aimed to say the GFM is worse than the GFL. It's not, it's just the way you tune it, okay? So both are useful, both can work, both are perfectly fine. I'm aiming to use this tool to design other controllers, not the ones that I already have, okay? But it was an exercise of modeling, okay? So when you do modeling, the control is not the priorities, how you actually define the quantities. And that was a way to say, okay, you can always define a sort of classical model with an internal AMF and internal frequency of anything. Then that model can be complicated, it can be strange, it can be with coefficients that are time varying, but you can, okay? And that could be the way. Okay, so in principle, you can implement a generalized model for everything, and then specifying what this coefficient is, just depending on the model. That could be also another way to do it. The problem is that in some cases, you need the control equations to know what to change in the parameters of this simplified model. So sometimes it's not very useful. Okay. Yeah, more of the same. So with the internal frequency, we can do controls, or we could do controls that are stable or better for a larger range of the values of the parameters. Okay, that's the only information. Okay, let's do. Let's move on some other example. Okay, so this example is on control. We forget about the internal model. Okay, now we measure omega. We measure the voltage. So in theory, if we need it, also we can measure rho. How do we use this to do better controllers? Okay, so the first thing was we have seen these equations that were linking omega and P and Q, and rho and with P and Q. My conclusion was that if I'm in the same time scale for the voltage and frequency control, maybe not just that it would be more complicated to decouple the controllers, but the controllers are so coupled that maybe it's better to take advantage of it instead of trying to decouple them. So that is the first example that I'm showing. It's not the most efficient way. It was just the simplest way. So I told him, just do the simplest possible thing that you can imagine. So what he did, I'm sorry that the picture is very small, but the idea is we have one channel for the frequency control through P, one channel for the frequency control through V, and then one channel of the frequency control through Q, and one channel of the voltage control through Q. We can activate or deactivate every one, or so using all of them, or only a combination of them, and so compare them. So I will call FP the control of frequency through P, then a VP with obvious meaning, and then FQ and VQ again with obvious meaning. All right, and then we can do FP, VP, FQ, VQ control all together, or only, for example, the conventional one would be FP, VQ. That would be the conventional control that we do. But only all combinations could work. Okay, so we tried all of them. Then there was the problem. I say, okay, we obtain results. They look with ups and downs. Okay, how do we evaluate if a certain set of controls is better than another? So we needed to come out with a metric, okay? And the students came up with a very good idea. Said, let's use as a metric the complex frequency, because at this point we don't have only a control that can regulate only the frequency or only the voltage, but maybe they can do all together. So it's not because the frequency is a little bit worse than maybe the control overall is better. We need to look at the overall effect. And so instead of looking at only omega or only V, we look at the combination of two. And since the best way to compare them is to have the same units, we use the complex frequency because rho as the unit of the frequency, right? So, okay, these are the various notations. FVP is, doing both omega and V control with P. FVQ is both VQ and FQ controllers. Okay, and this is the metric. Then instead of taking the metric itself, we integrate it. So it's an integral measurement, so increases on time. So the idea is that if the control is not very good, the deviations will be bigger, and so in time there will be a bigger value. So we are looking at the smallest mu will be the better controller. Okay, that's the idea. So this that is the way the metric works.
Can I have something?
Yeah.
Because here you can have rho and omega increasing.
Yeah.
And for different controllers, you don't necessarily could have the same values of rho.
Yeah,
maybe you want
that's the point. That's the problem. That's why. So for every bus, we calculate the metric.
Then you don't know if the bigger integration is going to be the worst or the best.
No, we know we wanted that overall, once you finish the simulation, the deviation of rho and omega are the smallest possible. Yes. Yes. You're worried about the actual operating point that can be whatever.
Yeah.
No, but there are still controllers that regulate V. The controller regulates V. It's not regulating rho. It's regulating V. So we are doing what we are expected to do. We want the voltage to be closest to the reference voltage and the omega to be closest to the synchronous frequency. What we estimate for a quality evaluation is this index, instead of looking only at omega or only at V during the transient. So locally, there might be variations that are bigger, but then overall, if rho is smaller, it means that the voltage deviated the least. And so at the end, since we do the integral of a derivative, we still have basically the same information as the quantity. Okay. So here we compare the original system. That wasn't the worst, because the worst is when we use a system where we substitute the single machines with theirs, and theirs do not do control, obviously, because we lose capacity of doing control. Then the classical controller was this FPVQ. And then this one, the black one, okay, the solid line is when we do everything with everything. So we do FPVQ altogether, okay? And you see the index, well, this is the coil, so you see that the frequency of the center of inertia deviates the least, okay, with respect to any other combination. So the contingency is the same, the system is the same, and just activating or not these channels in the controllers of the DERs. This is the voltage. So you see the black line is always the lowest or closest to the low. Now, I'm showing examples that are particularly good to promote my case, okay? Because there were many simulations where there was almost no difference, okay? But the black line, if it wasn't the best, was equal to the others. So there is no harm to do the control in the way like everything with everything, because it wasn't never worsening the dynamics. So you could, in some cases, obtain basically the same result with a classical control. There are some situations, like the ones that I'm showing, where the classical controller is performing worse than the proposed control. So this everything with everything. So it's never harming And it's so simple to do because at the end it's just adding an additional signal into the controller. It is based, one of the major problems with this paper during the review was there was clearly a control guide. It was saying, yeah, but you are proposing just a low pass filters for the controller. Yeah, that's exactly why I'm proposing this control, because it's exactly the control that people in industry may understand and maybe they even use. If I'm starting to, and then they will say, but by the way, if you want to propose a complicated control, do it. It's compatible. I'm just saying that how to use the signals, not no. So if it works with a low pass filter, maybe it works even better with whatever complicated control that nobody uses you want to propose, right? So, okay. So that's the point. So it's just a signal utilization that is different, not the control. And here again, we have, okay, here is not solid, is with this for dots, but again, is the lowest. Here is the index, okay? So the index you see is integral, so it's always increasing. If the error at the end is not perfectly zero, but here we wanted to check the combination of, we're saying, okay, we do some of the DERs with a classical control and some of them with everything with everything. It was always better or not worse to use the everything with everything. So another point to, okay, we don't need to mix up. It's just fine to do all the time. This is the effect of if the network is more resistive, so distribution systems. This is the classical transmission. This is with distribution. Now the difference is they change because of the network, but tends to be more efficient. So you see that when a raw or is similar to X, then the index is always lower. Okay, so the efficiency of this control improves in distribution system. This is and this was the effect of the penetration of DERs. So 30% of DERs, 50% of DERs, and different kinds of controllers with everything was at least always stable, but typically better than the other. So smoothing faster the oscillations, not unstable, if others could be unstable, etc. So conclusion, it doesn't harm, and in many cases, it can actually help. Now, I have a student that is trying to work to a perfection in it, because we are not really addressing these components P1, P2, Q1, Q2 that I described. Here we are just injecting P and Q, but with a control that takes into account both omega and B variations. So the next step is to do a sort of a vector control that takes into account and actually calculates P1 and P2, Q1 and Q2, and try to actually do the right thing. The problem is that it's 4 quantities and we have only 2 measurements, V and omega. So we don't have a degree of freedom of decoupling P1 from Q1 and sorry, from P2 and Q1 from Q2 completely. We can do something, but not complete. So this is what my student is working on. Okay. Okay. This is another application, and this application is okay. And this is very related to the question: should we measure the frequency locally? Is it important to have a local measurement of the frequency? Okay, rather than no, apparent. Okay, we cannot. But say that we can measure only the omega of the coil. Would it be better to have only the omega of the coil to do all the controllers? Provided that you can actually define it, because if you don't have machines, so who knows what it is, but okay. So this was strangely an undergraduate project, okay? So it was a student that I told the student, look, try, okay, let's see what happens. And nothing came out. At some point I said, look, let's try the following. So we've seen this yesterday, okay? And these are in coordinates DQ, omega, and rho. Okay, so we saw this in the discussion yesterday when we saw the transformation. So you see there is omega 0. Omega 0 would be the synchronous reference frame. Okay, So this would be 314 radians per second at 50 Hz. And this is the deviation with respect to that. Okay, fine. This is only local because there is no reference. So we want the voltage just to be constant at the end of the transit. So there is no V0 here to add to this component. Okay, so rho substantially is only a transient component. Omega has a transient component and a constant component. That is this reference. But we also know that omega and rho are invariant. So it doesn't matter what is the reference frame that I'm using to calculate it. So it can be a reference frame that is rotating at omega 0, or it can be a rotating frame that rotates at the omega of the coil. The result has to be exactly the same. The components are different because it depends on the rotating reference frame. Who knows what they are? Because locally, we cannot really measure omega coil. But I don't care because I can still measure or estimate this independently from the coil. I just measure B, basically, okay? And I can calculate it. So I know that though I can write it in this way, assuming that I know this omega coil, then this would be the deviation with respect to the omega coil. Now, I won't be able to estimate it locally because I don't know omega coil, but I know omega and I know rho. And rho is going to be anyway rho independently from what is the omega that we use for the path transform. So substantially, the conclusion is the following. I have a local quantity that will be always local, and another quantity that depends on the trend, whatever is doing the coil, this slow transient that typically you see for the coil, many seconds. On top of it, these are the oscillations that are local. Okay. Now, since I cannot measure this, so I cannot know this separately, but I can calculate this. So I told the student, okay, let's try to, let me see if I find the equation. Let's try to do this. So we use the omega that we estimate, so which is the local frequency, and then we subtract a quantity proportional to rho. So we can tune with this K the amount of local oscillations that we take into account or not in the signal. Now, does that make sense? Sorry if I go back, but kind of, because then think of hypothetical transient when you describe the transient this way. So it's an oscillation that is damped. So it's a typical electromechanical transient that you have. Then you would have that you could express the VD and VQ in this way. And then calculating omega minus omega coil, you would have this expression. And for rho, this expression. See, they cross sine and cosine. But these two coefficients, because of typical power system transient, are typically in the same order of magnitude. So these two quantities, the variation of local variation of omega and rho, tends to have a similar behavior. They might have a little bit counter shift in the phase because of these two magnitudes are not exactly the same, but they're very close. They're very similar. So we can, with the K, tune the effect of the local oscillation without knowing what is the omega coil. And so that was the added value. And I told the student that try. Okay, I was desperate because it was already March, and she had to submit the report in April, and we didn't have a result. And so I say, let's try. And somehow it worked very well immediately. I don't know. It was so. Of course, you need to tune the K, but it works super well every time. If nothing else does not deteriorate the time, but it always improves it actually. So of course you need to tune it right. Okay. Sometimes, and this is kind of a little bit of an issue. Sometimes it has to be negative. Sometimes it has to be positive. This case. Okay. But once you find the right sign, it's always working well. And if you find the right magnitude, you can optimize this response. And this. Now, sometimes it's not super effective, but it dumps better the oscillations, okay? And probably you don't see it, it's very pale, but Yeah, here is probably clear. So this is a case where it was small and negative. But once you find the right number, it's the same for all the DERs, and it's the same for any possible contingency in the network. So it depends pretty much on the network, I think. Yes.
Just a high level, long time ago, I saw something about the ultimate whole approaches that also come up with, and it seems to be in a similar look at the relationship.
I
Because
remember.
it could be, because I usually think love, very nice, but it's too complicated for me.
Yeah.
And but there might be actually a link between, because in the end you're also kind of looking at an energy.
Could be. It could be. I also skip the papers on that one because I know, it's like only sufficient but not necessary. So I say, okay, I don't care. And I never read it. But in control is a big deal, right? Because in control you can minimize the residual, so it doesn't matter, if it's sufficient and necessary or not necessary. But yeah, I get you. Yes.
It might be linked. It might be a different representation of something in that direction.
But look,
if you can do that, it will be hallelujah and
in control, what you are doing at the end of the story is always minimizing the residual. And if you think of it, the system can be stable only if the end is minimizing energy. So that has to be a link all the time whenever your control is stable. So, but in this specific case, probably it could be shown in a nice way. Yes, I agree. I agree. I've seen recently a work that was showing an application of basically the energy function, right, and the propagation of oscillations in the network. I like that, and in this direction as well. I could do the same with the complex frequency, right? So it's interesting. Yes. But I don't have students to work on that, so you can try. Yeah.
You can tell people that it was a fantastic idea. However, I don't get done.
Okay, I will. I will put that acknowledgement. Yeah. Interestingly, so at the end of the the students did the report. She passed. Everybody happy, but we got a transaction paper on this. So it's not regarded that that's a transaction paper now. It's amazing. Right? The shipping is like 1 week before the deadline. So interesting. Anyway, positive aspects. It does not depend on the system. Sorry, it depends on the system, but once you define it, it's always the same value for that system. Which led me to think that it's probably strongly dependent on the topology of that network in particular. So, but I couldn't find a way to formalize this. And the concept is that since it's a topology dependent, you need to tune it for each network. It can be positive, it can be negative. It's not really, you don't know a priori, you really need to try. Probably the most important advantage is that it's inexpensive, because at the end, we measure the voltage anyway. Rho is a little additional calculation that is the derivative of the voltage as well. But once you measure the voltage, that is not a big deal. And then it's just an additional signal that you add to whatever control you already have. It's nothing more complicated than that. So it's inexpensive, I would say. And it does not make a damage once you tune properly K. But there is a wide range in which K can be set, and the control would be effective. If you want to find the best K, then yes, you need to look in this range and do many simulations. But it's pretty robust in the sense that allows a kind of flexibility. It's not so sensitive. Okay, so concluding remarks, we are living in a paradigm shift where the frequency plays a big role because of the move from synchronous to non-synchronous machines. We are still looking at solutions. So I'm in this process, right? Within along the process, there will be many proposals and many ideas, many things. Then probably the simplest one will survive, like as usual, Microsoft with respect to Unix. Okay, for some reason people prefer Microsoft. Okay, but at least it works. Okay, well, Microsoft doesn't. But okay. So, but we need to propose things. Okay, so this was one. We need to question the conventional models, I think, especially because the most critical part is the shift of the time scales. It wouldn't be a problem if the time scales would have been exactly the same. We would have the usual decoupling. But since the time scales are going to merge between frequency and voltage control, then we will have to change something, even if we don't want to, if we wanted to allow more non-synchronous generation. Now, are the conventional controllers adequate? Maybe they are, but maybe we can also do better. And so here again, I'm saying, look, you can do better without complicated structures, without communications, or not necessarily with that. Just using in a slightly different way the signals that you already have. And so all the controllers that they show were really inexpensive. I think that is a plus, not a minus, as the reviewer was saying. But okay. Yeah, but they published that, and the editor didn't care about the review. So you never have the chance to send it back to your final comments. Say, I was like, that's bad. And, but anyway. Yeah, we will see last time. But now I win. In the past, you could put the discussion. You remember, there is the paper by Park, where there is one reviewer that say, look, very nice, but is a mathematical construction, and nobody will ever use it. So I would like that also, to put the name of the guy that says that in some papers at least. But anyway. Then the other message is that there are many frequencies. Okay, so I think that this is another change in the way of thinking, because again, it's the time scale thing. We were talking with this one of your colleagues. The idea of this single node network with one frequency, because at the end everywhere is the same. It's true, but in a time scale of the primary frequency control of the machine. So if we move to a time scale of the inertial response, and in the past there was no control there, so it didn't matter. But now there might be control. So in that time scale, we have many frequencies, not just the standard frequencies, maybe also different frequencies, and that's the point of the complex frequency. Okay, we can use the rate of change of power, so this S prime, okay, as a tool to design control. Of course, it doesn't provide a completely new information. It's the derivative of the power. Really. But the derivative has more information. Differential geometry is all about doing derivatives of the derivatives of the derivative. Every time you make a derivative, you get additional information, right? So this is the first derivative, so it's the first level of information. But in fact, it provides a little bit of information, and those controllers that I showed were based on what they deduced from the equations. And maybe we need tools, not just designing new controllers, but tools like modeling tools that allows us to understand the direction to model how to design the controllers. So is there a way to have a framework where I can know what is the direction of the controller that I want to design? Now, for example, looking at the split for the power into two parts, one that depends on frequency and one that depends on voltage. We have a sort of different approach to the control, because it's not controlling only P, but it's controlling the part of the P that is actually affecting the frequency. Now, that is a change in the way we think of the control. Right? And so maybe we can get more efficient controllers. Okay, so yeah, then the final question is the first one. Is the frequency still adequate? I think, again, the answer is yes, but we need to be ready to accept an extension of the definition and thinking of it as a quantity that is different place to place, at least during the transient, for sure. Yeah, that's are some. This is the paper that this is the undergraduate student. So yeah. Anyway, thank you. Yeah, because I wrote the paper, I did the simulation, so I did the thing. Yeah, no. I couldn't use anything of the report that she wrote. Yeah. Okay. I don't know. I think it is also died during the way. It's really, I mean, it's yeah, but you know, in half an hour you consume what 10 batteries. Is the least sustainable object I've ever seen. Is it running?
It has battery, it works.
Oh,
Charge.
okay. Almost the least efficient.
Yeah, question. Actually, first of all, thanks for not one but two very inspiring lectures. This question is about this combined voltage and frequency control. Did you also consider a data combination of the work channels? So,
What do you mean?
right now, I think you just each channel has a coefficient of 1, but let's say you have to use one of them.
Yeah.
Like one and the rest.
That was the other review. Yeah. Okay, good for you. You know, I really think that the anonymous system is really good. With vindicative people like me would be a mess. But so what we did was we did the two scenarios. Okay, we did the two things. We in one case we used the parameters tuned the best we could for the conventional control, and then we tried switching on or off the other channels, and so having this combined control, and it worked better, the combined control. But then one reviewer was saying, yeah, but if you tune the best the controller, maybe you can get better some other combination. Okay, so for every single combination with making a lot of simulation, we tried the best possible setup for all the games. Of course, heuristically, because we didn't have this controllability tools. We did it, right? With many attempts, you find good. There weren't so many errors in the network, so we could do it. So we found the best possible setup for every possible combinations of the channels of the control. So different changing the games, right? And it was always the same result. Well, whenever you were doing the same scenario, same contingency, then the combined control was either the best or just within the best, with the best. So others could be good, but the combined one was never unstable, was never worse, was never creating oscillations that were not seen in other cases. Now, can you, with weighting the components, do even better? Probably, for sure. Yes, we didn't try that specific thing, but my feeling is that we would obtain a similar result. So either is probably the best using all together, or is not worse than all.
And then the other question was about some of the results that we showed. So in some of the trend things with the complex frequencies, there was a huge overshoot in the beginning. But then when you were showing the grid forming results, there were no overshoots. Were they also there, or not that clear?
I'm gonna say which one was there?
What's your
But it was the simulation for the system.
Yeah.
Maybe the one with 100%.
No, not that. What do you do?
In some of these.
Earlier for combined.
For the combine, no, but it was just for the modeling. Yeah, no, we were, no, but that was just an exercise. It's not, I'm not saying this is better than other, just it was a sensitivity analysis of the parameters, and some parameters are way out of the normal values, just to show their effect, because we wanted to show that in fact the effect was the one that we were finding with the equations. So we're saying, look, if you vary this parameter, you get this effect. But in some cases, it's not a realistic parameter. It's just to show, to dramatize the effect of the parameter. Okay, so these simulations are not to take as I would like to do that kind of control. This what is the effect into this internal frequency of that controller with that parameter. You need to interpret that in that way. Okay? Not to take it as how I design